So welcome everybody to Advanced Digital Media AAD 367. I'm Josh Vermillion. I know most of you and I recognize a lot of names. I sort of saw some folks on camera and it's good to see you again and it's good to be back after summertime. So summertime doesn't usually go long enough, it seems like, but here we are, August 23rd, Monday, and we're getting started. Something that I find very exciting. This is part of my research expertise is how digital tools both disrupt and augment the design process and the process of both designing and making architecture, you might say. When it comes to design tools, design software, CAD, but also the CAM side. So when it comes to digital fabrication and how we make architectural componentry, how it's assembled on site, and upping the game of the sort of complexity game, so to say, when it comes to making bespoke, performative buildings and architecture that are highly responsive to the environment and culture and everything else. So I'm Josh Vermillion, as I said. My email address is on the syllabus. Again, I'm very, I think most of you that have had me, I think will find I'm very accessible via email. I'm obsessive compulsive when it comes to that little red icon on my mail app icon on my phone, and people keep texting me and emailing me. Sorry if that, hopefully that's not showing up on the recording. Again, also the Zoom link is here for our meetings. We'll use the same link every time. It's not like I'll change that up on you at all. Description for this course, according to the catalog, is an examination of advanced geometric modeling, an introduction to basic parametric thinking, development of robust drawing typologies, computer-generated renderings, physical models, prototypes, and board compositions. So that's a lot of big words put together in one run-on sentence. But suffice to say, we're going to deal with and look at different ways that we can digitally model our ideas. We'll introduce this idea of parametric thinking and parametric design. And then we'll also talk about how geometry, or how design can be informed by geometry, i.e., how we construct both the drawings and the sort of physical buildings, along with fabrication and production concerns. So how we would actually make this stuff, right? As well as some sort of, performative criteria. So in other words, we'll be looking at things like sun and shading, and then making design decisions and actually how do we say this? We can actually measure the performance of something and then feed that data back into the design so that the design can actually respond to the performance criteria that we set, right? So it's this idea of leveraging digital information to augment what we do as human beings, as architects, in order to make things better, smarter, faster, and better built, right? So we'll be doing that. We'll also be generating certain types of drawings and certain types of renderings and certain types of models and prototypes along the way. Objectives: students will be expected to demonstrate and understand parametric thinking. Again, we'll talk more about this in a little bit. Along with the application of these skills using parametric design software, typically we'll be using Grasshopper, a little bit of Revit, right? Understand and design relationships and associations between geometry, performance, and fabrication. I think that's, again, really important. What you'll find is that now that we can design pretty much anything shape-wise, the question is, why would we do any of these? And what makes one better than the other when it comes to looking at one shape or form or outcome, right? And so again, we can start to talk about things like geometry and performance and fabrication, right? Performance is one of those words where we typically talk about that when we think about, let's say, we always talk about high performance car engines, for instance, right? Something that sort of successfully negotiates and optimizes horsepower versus fuel economy and acceleration and those sorts of things, right? So when we talk about performance of buildings, we talk about how much energy they use, right? Or how much available sun energy they can use without driving up the amount of heat that's generated on the inside. Or there's lots of different ways to sort of talk about performance, and we'll touch on a few of those. But the key thing will be, how do we begin to take these things, geometry, performance, and making, and use those and simulate those and complete that feedback loop between designing something and understanding the implications of things that we draw and model when it comes to how those things will actually perform in the real world or how they actually get built out of physical materials, right? Completing that feedback loop so that those considerations and those concerns actually inform the design process in an iterative fashion, a cyclical fashion. We'll use a variety of media and communication to demonstrate algorithmic thinking and problem solving. And then we'll develop, and this is again a very important thing to talk about, and I'll touch on this more in the syllabus later, but to develop a computational literacy for these sort of key concepts and procedures that we use in design software and parametric design that can be applied to a variety of projects, regardless of specific software platforms. And the reason I say that is because, you know, part of these courses is learning how to learn, right? And so, you know, I've come and gone. I mean, I've been in this business for a long time. It's stunning, actually, how fast time flies sometimes. And a lot of software platforms have come and gone in over that time. I remember when I first started, there was AutoCAD and there was 3D Studio Viz, which was, you know, a derivative of 3D Studio Max. And there was Form Z, which no longer or hardly exists anymore. And so on and so forth, right? I can go through like probably 30 or 40 different design softwares that I've used over the years, and I really only use about 10 of them now. And that is to say that that these things come and go and they evolve over time, right? And the key thing is that you develop a sort of literacy for being able to pick up new skills, to stay abreast of all of these new developments, and sort of stay up to date with your skill sets, right? And so that's part of what we're doing. Just to sort of demonstrate this, this was part of a slide that Shop Architects, I don't know if you guys have heard of Shop Architects, but their principal came here a few years ago to give a lecture. They're a pretty famous architecture firm in Manhattan. And he presented, this is Greg Pasquarelli, he presented this diagram sort of talking about this sort of weird ecosystem of different software platforms that they go through. And just, this was just one project, right? And so suffice to say, just as if you went to a construction site or you worked in construction and you have a tool belt and you understand that just there's no one tool that just does everything that you need it to do, right? Like you need more than just a hammer or just a saw or just a tape measure in order to get the job done. It's the same thing when we design and then also manage an architecture project, right? No tool has everything that we ever need. And so it's really about the sort of fluency between going back and forth between these various software programs as easily as possible without losing the fidelity of the information, right? And so you can see that, you know, when it comes to doing some things, they might be going back and forth between Rhino and Revit, right? And then they're measuring performance when it comes to daylighting with Ecotext and Radiance. And they might be going back and forth and making presentation graphics in Illustrator and Photoshop and PowerPoint and InDesign, right? Sometimes they go back and forth between AutoCAD and Revit, back and forth between a flat drawing and the sort of BIM model, right? They have to, when they want to do something that's not so easy to do in Revit geometrically, they have to go back to Rhino and then they can bring it back into Revit and then sort of Revify it, right? And so you can begin to see, and then further on down, right? Like when it comes to lots of, let's say, custom components and things like that, sometimes it's about sending these things out to Excel spreadsheet that can then be sent out to a subcontractor, going to Navisworks and Project Primavera and Outlook and some of those other sorts of like project management and just sort of being organized softwares, etc. Right? There's even, you know, taking something back from Revit back into Rhino, 3D Studio Max, preparing it for 3D printing or laser cutting just to generate a model or a prototype, right? To sort of mock things up at a certain scale. And so you can begin to see that there's workflows when it comes to documentation, presentation, fabrication, and then handing it off to a contractor, a general contractor, and getting all these things made and built and assembled, and then stamped off and punch list. Okay, so you can begin to see that again. There's no one tool that sort of does everything, right? It's about, again, a literacy so that you can go back and forth between a number of different tools. All right. So I'm just going to read at you again for just a little bit here, and bear with me, but I did take some time to sort of craft this introduction. And so I think it's worth sort of reading through this with you and discussing this a bit. This course introduces advanced digital media to design students. So why differentiate digital design from other ways of designing? I think that's the key question here. I think that hopefully this course is eye-opening and illuminating when it comes to sort of opening your eyes to this larger question, right? Of how we shape our tools, right? But then the tools that we use begin to reshape what we do, right? And so, when we first brought on computers, let's say with AutoCAD, it was mainly just sort of automating some of the things that we could do with a pencil and pen, right? What you can begin to see is that we're starting to leverage computers and digital technologies to do things that we couldn't do feasibly with, let's say, paper and pencil, right? And so I make that distinction here, right? A digital design process leverages computational platforms, so our hardware, our laptops and our desktops, as well as software platforms and data, right, to negotiate and generate and to manage our design information for us, right? Now, back when I first started architecture school, we did this out on our desktops with trace paper and vellum and pens and pencils and sketchbooks, right? Now we have files and we can begin to sort of manage this stuff, with our computers. But in order to successfully wield these platforms in the pursuit of our design goals, we must understand some unique aspects that they provide to the design process, right? So I think in this case, I'm making a comparison or differentiating, let's say, that recognizing the differences between computer and, let's say, a pencil, right? Now, I love drawing with pencils. Don't get me wrong. And some of you had me in second year last year. No, just how far I can take a simple pencil drawing, right? You guys are probably having nightmares right now, right? So anyway, but it's easy, I think, to recognize the differences between, let's say, computers and a pencil, right? A pencil is still great at certain things, right? When I need to get an idea visually out on paper very quickly, right? Pencil is the easiest, simplest, quickest, most efficient way to sort of tactily, get my ideas out and scribble them out, whether that's jotting down notes, whether that's making a quick sketch, whether that's thinking aloud, right? That's the sort of key thing here, right? That's something that's very, very, very quick, right? And again, it's tactile, right? And it's very intentional, right? I'm guiding the pencil as I go, right? So there's that sort of brain, mind, eye, and hand working in a sort of three-way conversation, right, back and forth. But I think computers are good at different things, right? That pencils aren't good at, right? And so I think for instance, we can go through some of these things. Sorry, I'm losing my place here in the text. I'm just going to sort of use my cursor and select a certain portion of the text here. So they execute and they can re-execute rules very, very quickly, and they can remember those rules and the order of those rules also very quickly. They crunch numbers at incredible speeds, right? They can store and recall associations, geometric information, the relationships between different pieces of geometry, metadata, procedural histories, whatever you want to call these things, right? We can undo, we can redo, we can go back into this history of what we did and edit it, right? With these specific abilities, computational tools allow us to design complex systems, right, that simply aren't practical or even possible to generate and manage with pencil and paper. And so right now I'm sort of planting a flag in the ground and saying, we're going to be doing things in this class that you can't do feasibly with a piece of paper and a pencil, right? And so these abilities also bring about a different nature of interaction between, I would say, the designer and the computer as a tool. Remember, we just talked about our relationship, let's say, between our mind and our hand and a pencil, right, and our eyes, right? But when we use a computer, there's a sort of different set of relationships here, right? And it's one in which I would say we're not guiding, like I would with a pencil, things directly necessarily, right? But it's one in which we sort of relinquish some of that control in the direct shaping of form and order, right? What we're doing is we're actually creating a set of relationships, histories, rules, and parameters in order to sort of govern a system that can create the sort of architectural proposition that we're looking at, right? Can actually help us design. And so it's almost like a partner. As a tool, it's a sort of partner or interlocutor, right? That augments what we do. So sometimes instead of just sort of guiding and making something, making form, right? We're actually finding form or discovering form. And sometimes the computer helps us see things or generates things that we couldn't possibly have even imagined might be possible outcomes or solutions to the problems that we're designing around, right? Okay, and so I know I'm talking a bit abstractly here, but I think this will start to come into focus over the first few weeks of the class. These tools aren't as haptic, right, or tactile, right, as our analog components, right? And design isn't produced by the direct manipulation of tools by the hand, but rather they're mediated by the mouse, by sometimes it's syntax and writing actual program code, things that work at the machine level. Okay, but nevertheless, I would argue again that this process is still relying on a feedback loop, right? Where we generate things, we have to very carefully and critically evaluate them, and then we go back and regenerate them. So this is still an iterative process, right? But one that's augmented so that we can make more iterations and test more versions in the same amount of time. In other words, it gets us closer to something that's better, right? When it comes to the sort of design process, right? It sort of speeds up the process so that we can do things that are more complex and are capable of performing better. Right? And so I hope that this course presents a feedback loop and informed design process of iteration as both something that's instrumental for you that you can absorb and immediately apply in your studios, but also as a sort of ethos, right? That you continue to sort of develop over your time here at UNLV and in school, and then out in the professional world. Okay. And to just demonstrate or talk about this a little bit, let's just talk about who wants to tell me what this diagram is of? Can you guys see this diagram? Who knows what this diagram is based off of the architectural history? Anyone?
Is that just different diagrams of the different types of columns?
Columns, yes, they're columns. They're the classical orders, right? The classical orders, right? And so we have Tuscan, Doric, Ionic, Corinthian, etc. Right? And so the Greeks were the original parametric designers, right? This is a rules-based system in which there's a set of complex geometric relationships between each part of each of these orders, right? And so let's say the height of the column dictates the radius, or the sort of, not the radius, but the circumference and the diameter of the column, right? And then the distance of the number of columns, let's say the distance that that we have columns defines the number of columns, right? And then let's say the height also dictates the height of the base, the proportions of the base, the proportions of the capital on the top, etc. Right? And so you can see that there's all these relationships, right? You know, one of these, right, is 2 1/3 of these, right? And so on and so forth, right? There's all these sort of rich relationships between height and distance and quantity, right? That can be expressed in terms of parameters, right, or variables, right? So this is very much a parametric design problem. And you'll find that when I'm talking about parametric design, you'll sort of say, well, I've been doing this for a long time. I just always taken it for granted, right? And here what we'll do is we'll actually be designing and generating design systems that then can produce all kinds of different results, right? So digital media should help create rich generative design environments with multivalent results. Tied to data, information, and rules, digital media, and specifically parametric design, facilitates a design process that incorporates and negotiates many different types of information and constraints, whether we're looking at site or program or performance, just to name a few. And this data has to be managed, organized, and visualized in order to make use of it. Computational tools are fundamentally different from the analog tools that we've relied on for so long, yet these different types of tools are not mutually exclusive. That's a very important point as well. I still like pencils, don't get me wrong, right? In fact, you will probably have to sketch frequently for this class, right? It's easier to sort of sketch some ideas out on paper before you try to get into Grasshopper and start to connect up a bunch of nodes and try it out, right? It definitely does not have to be about any kind of aesthetic or formal agenda as well, right? Check this out, right? Zaha Hadid and Greek architecture, right? Both are somewhere along this continuum of parametric design, right? It doesn't have to be about some sort of weird aesthetic or formal agenda, in other words, okay? The tools and concepts we're about to explore are used by serious people in the design, engineering, construction discipline to accomplish very serious and complex projects. So I'm ready to go run with this. There is a suggested textbook. You do not have to buy this, right? This textbook is available. It's a book I wrote. It's available in the library if you ever are curious about looking at it. If you have the means to buy books, I do recommend starting a library of books. Then feel free, if to look at the library, and if you think that would be useful, then buy it. But by no means are you obligated to buy a textbook for this course, okay? And you need this software, right? So Rhino 7, Autodesk Revit, and then the Creative Cloud primarily will be using Photoshop, Illustrator, and InDesign in this course, okay? Rhino is the larger hit. If you, for some reason, don't have that from 267 in second year, again, there's a 90-day trial version that's fully functional to float you for a couple of months. Or if you need something really badly, the computer labs here in the School of Architecture also have Rhino on them. They also have Revit. They just take a little while to log into, I think, as well as the Creative Cloud. So prerequisites 267. I think you probably had that in the last few years, so I'm not too concerned about that. Course format and delivery. This course meets on Mondays and Wednesdays. And so we'll be doing some things on Mondays, then doing some things on Wednesdays. Then you usually have a bunch of stuff to do between Wednesday and the next following Monday, right? When you have some time and some space to breathe, and you don't have me sort of looking over your shoulder or virtually talking at you in Zoom, right? Let's see, we're going to be doing, again, I record every class lecture if I think it's going to be useful, and then I post it to YouTube, and then I embed it from YouTube into Canvas. And that way the modules on the Canvas site, right? So if you go to, let me just go to it here, bring it out without losing my place. So if you go to 367, if you go to the modules, today's the introduction syllabus, there's an introduction page. We'll talk about that in a moment. Then you'll see project 1 that goes from now until the end of September. What you'll see, the pages underneath become an outline and a sort of agenda for us. And so day to day, you'll see what we did and what was assigned and what was due that day, and that sort of stuff, right? So that becomes a really helpful way to sort of organize also the class content and recorded lectures and demonstrations and things like that, okay? And so I think what you'll find is that you'll just go to the modules page for this course, and then everything's right there as a sort of course outline. So we'll be talking soon about project 1, right? Which is called Generative Lattice. We'll be talking about trusses. We'll make a truss, then we'll make thousands of trusses, then we'll make a bunch of trusses that can change their shape and components. And then we'll, as you move a couple slide bars, and then you'll pick one, you'll bake it into Rhino, and then we'll start to bling it out in Photoshop and make it a sort of immersive perspective, right? And then for project 2, right, we'll talk about not only parametric design, but also digital fabrication, and we'll have these sort of grid shells, and then here's a sort of matrix of, I always photograph all of these when you submit them, and so we have this grid of like all of these sort of grid shells, laser cut out of chipboard, with all of these sort of performative sort of shading components that are all differentiated across them. And so we'll be talking about fabrication and performance in project 2. And then project 3 runs that sort of last month when everybody is really super busy. I know the studios are sort of backloaded and you get busier and busier. And so this course is more front loaded. And so project 3 is a fun project, in which case we use this sort of generative algorithm to generate things in class. You don't have any outside work. You can do all this stuff just during the class meetings if you just show up every Monday and Wednesday mornings. And what we do is we generate a sort of set of city blocks based not off of the sort of Jeffersonian grid, but off of a sort of what we call a cellular automata. So what we do is we take these units and then we start to grow architecture from them, right? And then they start to grow amidst not only to make new architecture, but also they sort of grow and are grafted onto these sort of hypothetical city blocks with existing buildings, right? And then we start to do things like generate axons, and then we start to place all of these city blocks and create a sort of generative city, right? This is called, what do I call this one? Urban cellular aggregations, right? So we're aggregating a bunch of units into some sort of larger whole, right? And using the generative capacities of our software in order to sort of create a city based off of the rules that we set for it. So that'll be a fun thing that'll then let us, again, go through the motions of some Illustrator line weights work, compositing line work from Rhino and some rendered raster graphics from Rhino and starting to put those things together. Okay, so attendance policy, please be here every time. I understand sometimes life happens, and no less when we're in the middle of a pandemic. And sadly, it seemed like maybe we were starting to get to the light at the end of the tunnel of the pandemic, and slowly that's not the case, apparently. And so again, if you're gonna have to miss a class meeting, just let me know, okay? Just email me with a great excuse. And if it's a legit excuse, then you know, we'll coordinate getting you caught up and stuff like that. But suffice to say, you know, attendance is really important. We're doing lots of new things every time. And I don't like you to miss out on things. I don't like you to miss out on the idea or the ability to ask me questions or to stop me and make me pause and redo something just so you understand it better, okay? Related to that, let's talk about this course. Under this thing called digital notes, computers sometimes crash. Sometimes computers like physically crash. I've seen it all. I've seen, like, you know, I'm waving to somebody, like I'm walking out of the parking lot to the building. I see a student, they wave, and then suddenly like their laptop like slides out of their backpack and crashes on the ground and falls into bazillion pieces, right? I've seen people sit on their laptops accidentally, you know, when they have it sitting on the chair and it's, you know, just playing some music on Spotify while they're doing something on their desk, and then somebody comes and sits down and didn't realize that there was a laptop there, and then suddenly the aluminum MacBook Pros like bend. It's really weird, right? Things happen, right? Please be sure to back up your work, right? Develop the muscle memory to continue to hit Control or Command S to save, and then every week, if not more often, please back up. There's no excuse for not backing things up, either to a physical external hard drive or to the cloud. You have unlimited storage at the moment with Google Drive via your unlv.nevada.edu account, right? So please, 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 for the rest of your life, try to engender some of these good habits like file management, naming things, keeping things in certain directories, backing those directories up weekly, right? You know, it's something you can do Friday, right? Like Friday, open up my laptop, hit the backup button, you know, time machine or whatever it is, and then do whatever else I want to do on Friday while my laptop backs things up, right? Whether that's going out, whether that's taking a bath, whether that's, you know, just chilling and watching TV or whatever it is you guys do on Fridays. I don't even want to know, okay? And look, sometimes this isn't the only sort of frustration that happens, right? Software keeps crashing. Your operating system gives you the blue screen of death, or won't boot, or has to boot up in safe mode, right? Or the computer just physically gets beaten up, right? But there are other ways to think about this, right? And you'll get to this point. Sometimes this might say my grasshopper recipe works. Other times it might say my grasshopper recipe doesn't work. And I have no idea why, and you stare at it, right? It happens, it happens. Learning to use these tools is hard. There is a very, very, very steep learning curve. And some of you will get this pretty quickly and others won't. It'll be a real true learning curve, okay? And I'm here to help everybody who's blowing through this material very quickly, and those who really need a little more time to get through it, to understand it before things start to click and sort of snap into focus, okay? In fact, most of you, I'll just say this, I don't mean to alarm you. I don't want you to to get sad or anything. But in fact, most of you at some point over this semester will probably feel lost. You might completely fail at something, right? Okay, don't panic. That is perfectly normal. I've been doing these things for a very, very, very long time, and I get stuck sometimes, but I've seen it all. Okay, if you are a whiz kid and you've never gotten stuck before, and then suddenly you feel lost, you're not alone. Okay, so don't panic. Just tell me. Just tell me. Okay, failure just means you're being challenged intellectually, and that's not a bad thing at all. Okay, that's not a bad thing at all. Don't be afraid of failure. We have to learn from failure. Okay, so don't be afraid of it. Okay, this course is specifically scaffolded as a crash course. We're going to go over lots and lots of things, but the most important thing to remember is that I just ask you to try your best, and if you do, you'll probably fail often. Okay, you'll figure out how not to do something several times before you finally figure out the way to do it. Okay, so the mantra, which comes from the Skunk Works: fail early, fail often, right? And that's just, I think, a kind of a mantra for design, honestly, right? We do lots of things. We evaluate lots of ideas, and we end up throwing a lot of it away, right? Before we hit on something that I think works well. Other times things make perfect sense while following a demonstration in class. But then when back at home, nothing works the way it did when I was showing you on the screen, right? And this, to kick it all off, sometimes to make it even worse, this usually happens right before a deadline when you're in the most, when you're in a big hurry, right? When you need the technology the most is when it's fallible, right? You forget a step, there's an error message that keeps popping up, or just things aren't looking right. It just looks like a total cluster. Just remember, right? When you're learning and you're trying new things for the very first time, adversity is normal, okay? You're gonna get frustrated, right? And that's just a symptom, again, of opening your eyes to a larger world, right? If you don't find some of this adversity, you're probably not trying hard enough. Let's just be honest, right? You're just playing things too safe. So overcoming adversities and problems are skills in and of themselves to be developed, right? The short-term goal, of course, is learning a lot of in and outs and specifics with Rhino and Revit and all that stuff, right? But the long-term goal, and I think is more important, honestly, in the long term, is learning how to learn. Softwares come and go. They evolve or bought or rebranded, combined. So they sometimes they just disappear entirely, right? Your ability to adjust, to adapt, to evolve with the times, right, relies on lifelong learning. I'm not always going to be there. I'm not always going to be your instructor to answer your questions at 10 p.m. the night before something's due, right? And so being able to figure out where to go for answers, how to figure out these things, right? To simply make sense of, or be able to read software interfaces, to answer questions, to overcome a problem you're having, right? Those are things that's why we want to develop your digital literacy. And that comes also with doing things that sort of pique your intellectual curiosity, right? And so this comes to the very last part, which is practice, practice, practice. Practice doesn't even make perfect, but it makes better, right? Let's just be clear here. Watching a YouTube video, I know it's cliche, is not research, right? Everybody says that. Watching a YouTube video will not make you an expert craftsperson, okay? Practicing will, okay? The more you practice, the better you can wield a design tool with intention, dexterity, and expertise, right? So developing this sort of sense of craft, the craft of making drawings, the craft of designing a building, of architecture, right? That comes with lots and lots and lots of practice. To be honest, we only just scratched the surface of the things that we're going to be covering in this course. And so it's up to you to follow your intellectual curiosities in order to apply these skills outside of just this class. The goal of this course isn't just to get like a couple of interesting truss renderings and then a laser cut grid shell and then some more axons out of you, right? the goal is to introduce these things to you so that you can apply them immediately almost to your design work in studio and other sorts of you know, at work, at other courses, whatever. Okay, so that's the key, right? You have to be able to sort of turn that corner and be able to sort of practice and continue to develop your understanding as well as your dexterity when it comes to sort of applying these tools to design problems. And of course, this is what happens when I talk about the frustration, right? It happens to me too. In fact, more than once this semester, this will be my prep right before class, and then, and of course, I'll be blocking the Suez Canal, and something won't go wrong, or something won't go right when I'm demonstrating it to you, and when you guys are watching in class, and then the pressure will be on, and that just happens. Don't worry, right? Sometimes it's easy when I'm showing you, and then when you get back home and you wait a day, and then you open it back up, and you're like, oh, I don't remember any of this, and nothing's going right. Okay. But again, try your best. And again, when we meet, the key thing is, as I start to adapt more and flip the classroom, you know, the course times will be, there'll be more class time available for you to come with questions and problems, right? And have me address those with you in class time. And so you'll be doing things outside of class and then using the class to sort of troubleshoot and debug things. The grading breakdown is as follows. Okay, out of 100% of your total grade, 30% will be for project 1, 30% for project 2, 30% for project 3. That adds up to 90%. The last 10% will be allocated again towards attendance and participation. So if you're really terrible on attendance, right, you know, you can expect to see your grade to sort of reflect that a little bit here, right? So again, stay on top of showing up to class and being here and being engaged. And again, if you do need to miss a class, let me know. Okay. Usually these things are something where you can let me know in advance, and then it seems much more plausible, whatever excuse you have, right? And believe me, I understand there are times where, you know, you need to miss a class, and you know, everybody has their own complexities in their life, right? So I understand that, and I think you'll find that I can be flexible when I'm not taken advantage of when it comes to you know, when you have to miss a class. Okay. The semester is broken up into 3 projects that I mentioned several times now. Project 1, Generative Lattice, will start actually on Wednesday. We'll start it, and we'll go till the end of September. Then we'll start performing a grid shell. That'll go until the beginning of November, and then that last month or so, we'll do the urban cellular aggregations project. Okay. This subject might change, or sorry, the schedule might change. It's subject to change. I don't know why I said subject. The schedule will probably change. Now, the reason I say that is because these dates are, I mean, they look good to me, but you know, when we get down into the sort of trenches and actually doing this stuff, they can be kind of arbitrary, right? I'm never just going to push up a date on you for no reason, unexpectedly, right? So this isn't like I'm going to adjust the schedule as a sort of got you, haha, you know, sort of thing. I don't do that. It's not productive for anybody, right? But if we do need to speed something up, or slow something down to give more time to something that you're just not understanding as a class, right? I can sort of do that. There's some latitude in the schedule to make this really work, right? And I'll be honest with you, I thought first time I did this, you know, it's been a long time, but you know, I thought, okay, now that I have this sort of cadence down, I sort of know how things will flow together. But you know what? Every cohort is different, and every class has its own dynamic, and so, you know, honestly, I can, you know, there's latitude in sort of how we can adjust the schedule, because I think you'll be different than last year's and the year before that, for sure. Okay, so in other words, sometimes we might need to look and see how you're progressing, and we can adjust the schedule accordingly. Okay, the rest of this stuff, I believe, is boilerplate from the provost office. So there's a bunch of academic policies, student services and activities, university policies, and university community and libraries sort of stuff, right? And you'll see those at the end. If you're interested in any of those, right, you can click on those links and find out more. We're meeting remotely, so you don't even have to put on a mask for this class, unless you're sitting in a place where you need to wear a mask. I'm in my office right now on campus, but I have my door closed, nobody's in here, so I'm not wearing my mask. All right. So at the risk of glossing over any questions. Please save any questions or concerns you might have for the end, just because I'm recording this. And I'm just going to quickly open up Rhino and Grasshopper in this case in Windows. And I'll demonstrate a few things that we're going to be doing with some of the material from Project One, right? Just to sort of give you a better sense of what I mean when I talk about parametric design and using digital technologies in ways that are different than, let's say, a pencil. So what I'm going to do is I'm going to build a truss, right? We all know what trusses are. I hope so. You want to be an architect, it sure helps if you know what a truss is. So let me just demonstrate what a bow truss is. I'm going to have a sort of bottom string and a top string, and the top string is going to look like an arc, right? And so this looks like almost like a bow from a bow and arrow, right? So the sort of top chord is curved, bottom chord is straight, and I'm going to add this sort of diagonal webbing in between, right? And so these are all about structurally spanning longer distances, right? And so any weight that we put on this from gravity and live loads, dead loads, right, gets directed to the ends and then down to the ground on either side, right? And so trusses are a really nice way of sort of making some long spans across spaces, right? And so, you know, some sort of structure would be over here and over here. All right. And some of you might not know that yet because you're probably taking structures this fall and spring. But hey, congratulations. Surprise, we already talked about trusses. So you can tell Deborah that all that you know about trusses, and you can show her how you can make lots and lots of trusses in the Grasshopper here soon. Just going to go ahead and clear that out. Now that you sort of know what we're doing, right? Let's just think about this as a recipe. If I have a line, I can find a point along this line and draw a point upwards, right? And find the end point there. And then I can draw an arc between this point, and this point. And now I have the bottom chord and the top chord of a truss with only a line as the starting ingredient. And then what I can do is I can divide up this curve a certain number of times, and this curve the same number of times. These x's meaning points that I'm placing, and then I can start to connect the dots. I can start to draw lines between the points. 1 to 1, I can also draw the diagonals and make the webbing. And I can make the webbing in the opposite direction, right? And what I've just done is I've just sketched quickly with my mouse, which is really difficult to do, by the way. I don't know if you guys have noticed that or not. What I've done is I've sketched an algorithm, right? Sort of step-by-step set of instructions for how to take a line as an ingredient and then make a truss out of it. Yeah, not so bad, right? And I could do this manually in Rhino with some snaps and drawing and stuff like that, right? But I'm going to do this in Grasshopper, and you can just sort of see what we're doing here. I'm going to go ahead and clear that out. All right, but I'm going to go ahead and try to follow this as closely as possible. I have a line in Rhino, and I'm going to bring that in to Grasshopper so I can use it as an ingredient and build off of it in my parametric graph here. So I'm going to set one curve. I don't know what's going on here. Why this is, there we go. Set one curve. I'm going to select this. All right. Okay. Now I'm going to take this line. Okay. And again, you don't have to follow along. You're not going to know every single detail. But what I'm going to do is I'm going to implement that recipe that I just said. I'm going to find a point along that line. So I'm going to plug this into this widget, right? And what I'm doing is I'm scripting. I'm writing code, but without actually writing code, right? So I'm just what's called visual programming. I'm going to reparameterize this curve, right? I'm going to give it an address, right? So this is like a street address along an address along a street, right? Go from 0 all the way to 1. I'm basically placing a point on this curve, right? If I want to go halfway, like at the midpoint, I can double click. I can say 0.5. If I want at the end, I can go to 1, or at the other end, I can go to 0. All right, and now I'm going to draw a line, just like I sketched, from this point. Let's say start point, direction, and length, right? So there's lots of different ways to make a line, right? So this is just almost like have you guys ever bought the Nestle Tool House chocolate morsels, and then you look at the back, and there's a recipe for how to make cookies, right? And so it gives you a set of ingredients. It's like, okay, flour, eggs, milk, sugar, vanilla, etc., right? And of course the morsels, because they want you to buy the morsels. And then it gives you a step-by-step instructions with how to use and combine those ingredients to make cookies, right? So the inputs are the ingredients, then there's step-by-step set of instructions, and then there's an output, cookies. And that's exactly what we're doing, right? When we talk about an algorithm, right? It's a recipe. So what we're doing is we're taking an ingredient like a line, and we're performing a recipe on it to turn it into a truss, okay? And again, this sounds really silly, right? Like it's something that would be like, yeah, I've done this, I could do this. I could make this truss actually much quicker in Rhino with my mouse and just using these tools over here, right? But bear with me for a moment, right? So I'll use this as a starting point. The direction I'll use, let's see, the z-axis in the world Cartesian coordinate system here. And for length, I'm gonna make that a variable, right? So again, here's another parameter I can change, right? It's a variable parameter. I can use a slide bar and I can adjust the minimum maximum. There we go. Oh yeah, I can make that as tall as I want, darn it. Okay, now I need to find that endpoint of this line that I just created. So I'm just gonna use a widget that the ingredient is a curve, and then the output is the start point and the end point of that curve. So I can use that endpoint now. Yeah, okay, great. And I'm gonna do the same thing with this original curve that I had. Oh yeah. All right, great. Now I'm going to draw a curve of my own. I'm going to make a NURBS curve. No, you know what? I'm going to make an interpolated NURBS curve. There we go, interpolate. I'm going to plug in this as a vertex, and this is a vertex, and this is a vertex. So we have those three vertices, and now I've made this sort of bow, right? So now I have this curve, and I have this curve. At the top and bottom of my truss, now it's time to make the webbing. So I'm going to divide each of these up. Let's say divide curve. So a curve to divide, the number of times to divide the curve. Yeah, that sounds good. All right, so I'm going to divide this curve up. How many times? I'll make that another variable that I can adjust, right? The sort of parameter in the parametric design. So I'm going to constrain this to integers, set the minimum to 1, the maximum to 30. There we go. Yeah, why not? I'll do it there. I'm going to make another one of these widgets. I'll use the same number, but I'm just going to plug this curve in for this. We'll divide this up as well. And now we're going to divide it how many times we want. In each of those divisions, it populates these curves with a point. There they are. Now I'm just going to start connecting the dots, right? I'm going to draw a line. Is the shortest distance between 2 points. It's typically how we draw lines, isn't it? All right. Okay, and now I'm just going to diagonalize these things. I'm just going to take this list of points. I'm going to shift it over by one value. Wrap, and I set to false. And now I'm just going to make another set of lines. There we go. With this list and this list. Oh, come on now. There we are. Yeah, there. Now it's working. Go back here, I'll take my list of points. I'm going to shift this list of points one value over. Set this to false. This will make more sense later on, don't worry. I'll take this set and connect it up with this one. Now we get our diagonals. All right, there we go. Now we have a truss. And of course I could sweep a shape along here, a profile, like some sort of aluminum extrusion or steel extrusion. I could pipe them or whatever I want to sort of give these curves and lines thickness, right? Maybe they're pipes that are welded together or whatever. In fact, why not? We'll just do that right now. Pipe these. That radius seems a bit large. So let's make it, again, another variable, right? Yeah, I can adjust the radius as I go. And then when my structural engineer, when she tells me exactly what they need to be, I can just adjust it right here, right? And everything updates very quickly. All right, now we'll take these top and bottom chords. Let's plug those in. Oh yeah. All right, let's see. Oh, that was the wrong one. Here we go. Boink. And There it is, right over here. Right. And maybe this one's no, yeah, maybe this one's always twice the size. So we'll take whatever the radius of the webbing is, and we'll basically say x times 2. So take whatever that is and multiply it by 2, right? So now we have a relationship where the sort of chords are twice as thick as the webbing. And of course, we can update them all right here with this slider, right? So we can begin to make these relationships, whether they're structural or aesthetic. Right, so, and you're thinking, wow, that took a lot of time, right? So what happens if, let's say I wanted to make, instead of just one truss with one curve, let's say I had 30 curves that I needed to make a truss along. All right, so let's try that. Now, tween curves, start, and the number, sure. Right, so now I have 1, 2, 3, 4, 5, 6, 7, 8 curves. So I'm going to make 8 trusses. I'm going to say, instead of set one curve, set 8 curves, set multiple curves. Let's see what happens. Now it's going to mess up just a little bit here. And that's because I have a data tree. Let me see what happens if I just graphed that. And if I just, let me ungraft that and graft it back here. And let's see here. We have points here. We have points there. We need to break those up into, oh no, I'm grafting in the wrong place. 24, 24. See, again, I refer back to the syllabus. I'm having one of these moments, right? Okay, anyway, I'll fix this later, and I promise I'll show you. Let's say instead of just doing along 8 sort of separate curves, let's say I have a surface that I want to sort of divide up with curves and then populate, right? Let's say the surface can change its shape, right, based on its proximity to a point that I can move across the screen and start to change its shape, right? And so now I can do something like, let's see, like this. Oh yeah, right. So now I'm making even a 3-dimensional truss, right, across this shape. And all of these parts and components will change both, I can change all of these parameters, right? The number of times I'm dividing, or the number of sort of modules, right? I can also change the shape of the surface, which generates the shape of the curves, which generates the shape and length of the bow truss, right? Right. And so what we're learning basically is how to do things smarter, right? It's not like we don't work hard already, but we need to work smarter, right? And so parametric design lets us do that, right? In other words, when we go through the process of modeling all of this stuff, we do it once here, right? We make the recipe, and then we can plug in different ingredients each time, right? And then start to make and change the parameters, right? And instead of having to redo everything manually and take 10 hours for each version, right? We can spit out 10 of these in 10 seconds, right? So I hope that sort of helps demonstrate the value proposition here, right? And now we can do things that are complex. This helps us manage those. This helps us manage changes. This helps us also manage to not only make one truss, but let's say now we need to make 100 trusses and they're all different, right? So it has that sort of looping ability, right? That comes with scripting and programming, okay? And so when you put all of these things together, we're doing things that, I mean, it would be really hard, honestly. I mean, I wouldn't want to have to draw this in pencil, would you? First, you'd have to like figure out these splines and get the French curve out and then try to like measure across them and divide them up and then start connecting the dots. And you have so many points, it's like hard to figure out what you're trying to connect. And, what a pain, right? Right. And so what we're dealing with is stuff that can't necessarily be done with pencil and pen and paper, right? And I think it's important to remember that. And what I'll do is I'll show some examples throughout the week, in the next actually 2 weeks, where it starts to sort of lay out like why you would want, let's say, a truss that bends, or for each shading component in a window to be slightly different than the next, right? And so we'll talk about these things as we learn how to workflows for how to generate them and measure them.